So now it remains only to determine the n constant C1, C2 and Cn, etc. up to Cn. So we have to determine these constants. So for this purpose, we will make or we will find n equations involving these n constants C1, C2, etc. Cn and some calculable quantities by multiplying both sides of equation number 4 successively by g1 of x, g2 of x, etc. gn of x. That means first of all we will take the equation number 4 and multiply the first for equation number 4 firstly with g1 of x, then integrate from over the interval a to b. So we will get one equation involving C1, C2, etc. Cn, and then again we multiply this equation number 4 with g2 of x, then integrate from over the interval a to b. Then also in that way we will get n or we will form n equations. So first of all, for the first equation, we first multiply equation number 4 with g1 of x and integrate from a to b. So the equation will be like this. So integral a to b g1 of x into y of x dx is equal to integral a to b g1 of x into f of x dx plus the summation will be there. That summation you can see that lambda into is summation n equal to 1 to n cn into integral a to b g1 of x into fn of x dx. Now the left side it is C1. Integral a to b g1 of x y of x dx is by definition it is C1, or we denoted this integral as gn of x, integral a to b gn of x y of x dx as Cn's. So here it is C1, and then the first term, then when we expand the summation we will obtain lambda into c1 into integral a to b f1 of x g1 of x dx plus c2 integral a to b f2 of x g1 of x dx plus etc. The last term in the summation will be lambda into cn into integral a to b f capital N of x g1 of x dx. Now taking all the terms containing C1, C2, etc., Cn into the left, we will obtain this as um, um, 1 minus, that is here in the left side there is already C1 and there is a in the right side there is again one more term containing C1. So combining these two we have the coefficient of C1 will be 1 minus lambda integral a to b f1 of x, this term f1 of x g1 of x dx into C1. Second term will be minus lambda c2 integral a to b f2 of x g1 of x dx into C2, etc. The last term will be minus lambda integral a to b f capital N of x g1 of x dx into Cn is equal to, the only thing remaining in the right hand side is integral a to b g1 of x into capital F of x dx and name it as equation 5.1. Similarly, we can multiply the equation number 4 by g2 of x and we will obtain an equation involving c2, c1, c2, etc. like this. So in the left side we will have g2 of x y of x dx from integral a to b, and in the right we have this integral a to b g2 of x f of x dx plus lambda um, lambda integral sorry summation n equal to 1 to n cn into integral a to b fn of x g2 of x dx. So again as in the similar as we done in the first equation, we combine all the terms, common terms, and taking all the terms into the left containing c1 c2 etc c capital N, we have the first term will be minus lambda integral a to b f1 of x g2 of x dx. Then second term there is 1 minus lambda integral a to b f2 of x g2 of x into c2, etc. The term containing cn, which is equal to, in the right side we have integral a to b g2 of x f of x dx and we substitute as equation number 5 2. Now when we multiply with g3 of x and do the same like this, we will get a third equation and etc. The last or nth equation we will obtain as multiplying with the g capital N of x. So the left hand side will be minus lambda integral a to b f1 of x g capital N of x dx into c1 minus lambda integral a to b f2 of x g capital N of x dx into c2 plus etc. The last term will be plus 1 minus lambda integral a to b f suffix capital N of x g suffix capital N of x dx into c capital N is equal to integral a to b gn of x f of x dx and name it as equation 5n. So when we can see that all these n equations, there are some calculable integrals are there. Integral a to b, sometimes it is f1 g2 or f2 g2, fn gn or like that. That is integral a to b, some gm of x into fn of x like this. So we rename this or denote this integral as alpha mn. So alpha mn as integral a to b gm of x into fn of x. And in the right side of all these n equations, we have gn of g1 of x into capital Fx like that. So we name integral a to b gm of x into capital F of x dx as beta m. So we can write the a system of equations 5 in some simple form using alpha mn and beta m. So we have the equation system 5 can be written as, you can see that when we consider the first equation this will be yeah, containing C1, 1 minus lambda integral a to b f1 g1 x or g1 f1. So m equal to 1, n equal to 1. So this is alpha 1 1. So we have the first term will be 1 minus lambda alpha 1 1 C1. Now second we can consider that is this is into dx is the, so gm m equal to 1 fn n equal to 2. So this is alpha 1 2 like this is alpha 1 capital N, this integral. Okay, like this in the second case we have g2, this is alpha 2 1, this is alpha 2 2 etc. alpha 2 capital N like this, and this is beta beta 2, and the first one will be beta 1 I think. So this is beta 1. So we have the equations in the symbol form as 1 minus lambda alpha 1 1 c1 minus lambda alpha 1 2 c2 etc. minus lambda alpha 1 and cn equal to beta 1. Like this we will get n equations, or we can see that this is n equations in n unknowns. C1, C2, etc., Cn, and we have to calculate this unknowns. So this linear system of equations can be considered as a matrix form or can be written in the matrix form as, first we can see the coefficient matrix. We can see that the first term, the diagonal terms of the matrix, coefficient matrix are 1 minus lambda alpha 1 1, 1 minus lambda alpha 2 2, etc. 1 minus lambda into alpha n n. So, and all other terms are minus lambda alpha 1 2 like that. So, we can see that the coefficient matrix is of the form I minus lambda A, where A is the matrix Ij, or A is equal to matrix alpha Ij, or this is the matrix in the expanded form. It is an n by n matrix, and beta we can consider as the right hand side matrix beta 1 beta 2 etc. beta n, and C is the unknown matrix, or the unknowns to be determined C. So we can write the equation or system of equations can be converted into matrix form as I minus lambda A into C is equal to beta. Equation number 4. Equation number 9. So in order to talk about the solution of the solution of the integral equation, we know that the solution is of the form equation number 4, that is y is equal to fx plus lambda summation n equal to 1 to n cn fn of x, where the cn's are obtained by the nature of the solution of this. Cn's are obtained by the nature of solution of this system I minus lambda a into c equal to beta. So we have to check the nature of solution of this system of equations. So this set has a unique solution if and only if the determinant, we know that the equation is of the form some uh, bx equal to d, isn't it? I minus lambda a, we can call it as another matrix b, and c is the matrix, let it be x, which is equal to d is the matrix beta. So bx equal to d is in the form. So this non-homogeneous system has a unique solution if and only if, since all these are square matrices, this has a unique solution if and only if the determinant of the matrix B not equal to 0, or which is denoted by the symbol delta. So delta of I minus lambda A doesn't vanish. Then this system of equations will have a unique solution. Okay. Now, first case, we consider that or we check the solution when the f of x is identically equal to 0. So, if the function f of x identically equal to 0 in the integral equation, then that type of integral equations are called a homogeneous integral equation. So, the integral equation is said to be homogeneous. So if capital F of x is equal to 0, we can see that each beta, by the definition from beta m, the beta m is integral a to b gm of x into f of x is there. So if f of x becomes 0, all beta i's will be 0 for I equal to 1 to etc. up to n. Then if beta i's are 0, the matrix beta is 0 in equation 9, or in the matrix form, or the matrix equation will also be a homogeneous system of system of equations. So the homogeneous system Ax equal to, it is of the form I minus lambda A into C equal to 0, which is a homogeneous system. And we know that for a homogeneous system, there is always a trivial solution. That is, all Ci's are equal to 0 will always be a solution. So if all the Ci's are equal to 0, then substituting equation number 4, we have solution is in this form. So all Ci's are 0 means the summation will be 0 and f of x is already 0. So we have y of x identically equal to 0. So y identically equal to 0 is a solution of the integral equation also. So if the system is homogeneous, or if capital F of x is identically equal to 0, then equation number 1, or the integral equation, always has a solution, always has a solution. So that is y identically equal to 0, corresponding to the trivial solution of the system c1 c2 etc cn identically equal to 0. So in this case, that means in the homogeneous integral equations, that is, if f of x equal to 0, and suppose the determinant delta not equals 0. So if the determinant doesn't vanish, then system has a unique solution, and we know already that y equal to 0, or ci's, all the ci's equal to 0 is always a solution. And moreover, if the determinant doesn't vanish, then this will be the only solution. So all ci's equal to 0 is the unique solution of the system 9, or equations 8. Then the corresponding integral equation will have only y equal to 0, the identically equal to 0, as the unique solution. Now, if the determinant identically equals 0, or does vanish, then we can write at least one of the constants Ci in terms of the other, and we can choose one of them as arbitrary, and consequently there may have infinitely many solutions. Also, for the corresponding integral equation, we will get infinitely many solutions. In the homogeneous case, if and also if the determinant is 0. This is actually the nature of solution of the system of equations we are describing or we are discussing. And according to the nature of solution of the system, we will obtain either a unique solution or infinitely many solution or no solution at all for the corresponding integral equation. Now we were talking about the case where f of x identically equals 0 or the homogeneous integral equations. Now the values of lambda for which the delta of lambda is denoted by determinant I minus lambda a. So delta of lambda equal to 0. That means the values of lambda at which the determinant vanishes are known as the characteristic values or eigenvalues of the integral equation. And any non-trivial solution of the homogeneous integral equation corresponding to that value of lambda are called characteristic functions or eigenfunctions of the integral equation. These two terminology is very important. Uh, so, um, okay, so we have characteristic, we know what is characteristic values and corresponding characteristic functions or eigenvalues and eigenfunctions. So this about the homogeneous case. Now we assume f of x is not identically 0. Case 2, as case 2, f of x is not identically equal to 0. But there is one more condition is there. F of x, even though it is not identically 0, it is orthogonal to all the functions g1 of x, g2 of x, etc., gn of x. That means integral a to b gm of x into capital F of x equal to 0 for all m. 1 less than or equal to m less than or equal to capital N. So this happens. This means all beta m are 0, which implies in the system of equation the matrix beta. The matrix system is beta equal to 0. So then also we will obtain the homogeneous case I minus lambda a into c equal to 0. So as we already discussed in the case where f of x identically equal to 0, we will have the same uh, solutions. If the determinant is not equal to 0, then the unique solution is C1 equal to C2 equal to etc. equal to Cn for the system, and hence for consequently for the integral equation, the solution from equation number 4, the solution will be y of x equal to capital F of x, since it is non-identically 0. Not identically 0. So y of x equal to f of x will be the solution. Now solutions corresponding to the characteristic values of lambda are now expressed as the sum of f of x and arbitrary multiples of characteristic functions. Now we discuss if at least one of beta I doesn't vanish, then we have the matrix B is non-zero of equation or the system of equations 9. Matrix B is non-zero. So the equation system of equations will be a non-homogeneous system of equations, and we know that the system of equations has a unique non-trivial solution if the determinant not equal to 0, and leading to consequently the integral equation will also have a unique non-trivial solution if the determinant delta of lambda not equal to 0 or doesn't vanish. Suppose this vanishes in the non-homogeneous case. Suppose the determinant vanishes, then there may be two cases. Either they are incompatible and hence no solution at all, or the equations may be repeating, and in that case we will obtain infinitely many solutions for the integral equation. So these are about the cases. So we have discussed the homogeneous system case and non-homogeneous system case. So in the non-homogeneous system case, if the determinant doesn't vanish, then we will have unique solution. Suppose if the determinant vanishes, then we have um, two parts or two possibilities. That means one is the system is incompatible and no solution at all for the integral equation, or otherwise all the equations are repeating and hence there may be infinitely many solutions for the corresponding integral equation. So these are about the nature of solutions of the um, Fredholm integral equation having separable kernel. So this is about the theory to have these solutions in to have a unique solution, no solution at all, or infinitely many solution for the Fredholm integral equation with the separable kernels. For the now the illustration part we will do in the next lecture. So let's stop here. Thank you all.